Welcome back to the second part about the magnetic field that is created when you use a coil as an electromagnet. In our previous video we saw that if you wanted to see what the field was like of a coil, it acted incredibly like a bar magnet with a virtual north pole and a virtual south pole, and that was determined by the sense of the current that flowed through this coil. Now, in this situation, we actually have two areas that can be studied. The first area is outside of the coil, and the shape of the magnetic field is actually a bipolar field. A bipolar field, the same as you would with a bar magnet. However, when we look inside of the coil, you actually get a homogeneous field again. Why? All the field lines are technically perfectly parallel to each other, meaning the magnitude of the magnetic field inside of the coil will be the same regardless of your position inside of the coil itself. Now, outside of the coil, you will notice that the field lines are going away from the North Pole and towards the South Pole in this case. So in this case, this follows the traditional pattern of from north to south. However, when we look inside of the coil, the field lines are actually flowing from the South Pole to the North Pole. So it is the exact opposite, meaning we can divide our magnetic field up into two distinctive parts, outside of the coil and inside, and they both behave very differently. Now, when we will be discussing the magnitude of the field vector, we will be determining it on the inside of the coil, namely the homogeneous field created there. If we wanted to determine how strong the magnetic field is, what the magnitude is, we will be using this equation to do so. Now, what are the different parameters in this equation? We notice that our magnetic field vector is directly proportional to the current that flows through it. Now, this is annoying because the symbol of current and L, when you type it, a capital I is the same as a lower L, so that makes it difficult to understand, to interpret. Otherwise, it's going to look like we have the same symbol twice. So I'm just going to add these two to indicate that this is the current. The second thing that we notice here is mu. This is nothing new to us. This is the magnetic permeability of the substance in the center of this coil, and we knew that it is the product of the magnetic permeability should be a lower O in vacuum multiplied with the magnetic permeability of your substance, meaning the basic magnetic permeability mu0 and mu r, the relative magnetic permeability determined by your substance. For air and everything, this is close to 1. If you've got a ferromagnetic material in there, this will be much higher. Ferrite, for instance, 640 times as strong, as a simple example. The next things are also important. N equals the number of twists in your coil. And the second one that is mentioned in the equation is length, and this is why I actually adjusted my symbol for current. This is the length of the coil in meters in this case. N doesn't have any unit associated with it. Now, ironically, if we take these two together, N and L, we're going to be looking at the ratio of the two of them in our setup. This ratio, the number of twists in your coil divided by the length of the coil, can actually be described as the density of the coil. How closely packed together is this coil? Now, in order to explain this, I've got this simple exercise here at the top. When we look at this first situation, we have 6 twists in our coil for 1 length unit, meaning the density of the coil can be described as a factor 1. When we compare that one to situation B, this one only has 3 twists in it. However, it is only half of the length, meaning the density between these two is identical. The strength of the magnitude of the magnetic field will be equal between the two if the current is the same. And they both have a current of 1, meaning these two are perfectly identical and can be described as a factor 1 in this case. When we look at situation C, it only has half the number of coils or windings in your coils for 1 length unit, meaning it is technically only half of the density of situation 1. However, you do have 3 times the current, increasing the magnetic field. This one will actually be 1.5 times as strong, situation C, as situation A or B. When we look at situation D, you've got 6 coils, but for half the length of the coil, meaning the density is actually, in this case, twice as large as situation A. And it's got twice as much current running through it. In total, this would be a factor 4. The field created by this situation will be 4 times as strong as situation A. And if we look at situation E, we can count 9 twists in this coil, meaning you've got 1.5 times the number of twists in a length unit. The density is 1.5 times greater than situation A, and you've got the same current running through it. So also this one will have 1.5 times as much or as strong a field as situation A. So in which of these situations will you end up with the strongest magnetic coil? Consider the density of the coil first, which is the number of twists in this case divided by the length of the coil. Then consider the current I. If you take both of these into each other, or take these into account, the strongest magnetic field in this case would be situation D, which would be a stronger magnetic field than situation C, which would equal situation E. And these two would be stronger than situation A and situation B, which were identical in this case. Now, this is a simple introduction on determining the magnitude of the field vector. We will then be doing some extra exercises during the live classes that follow, which are explained here. We will be looking into them in more detail in a bit. I will see you in the live classes.